IBPSA-USA Building Data Exchange Committee webinar. My name is Tim McDowell. I'm one of the members of the BDE committee, and I'm sort of standing in as the IBPSA-USA host, which I just realized I was supposed to have a couple of standard slides to show, but I don't have them. So for anyone who's on this call and interested in this material and interested in becoming a part of IBPSA-USA or the Building Data Exchange Committee, you can please go to the website and you can find ways of joining both IBPSA-USA and the BDE committee. With that, I will hand this off to Nick Long to introduce the session.
Great, thanks Tim, and hello everybody. Thank you for taking the time today to come and hear about some advancements in building data exchange with IFC and semantic web technologies. We have three presenters today. We'll be starting off with Léon van Berlo with buildingSMART International. Joel Bender will be discussing semantic web technologies from Cornell, and Gabe Fierro from the Cara School of Mines, and NREL will be talking about BRIC. I'm going to provide some introductions of the presenters, and then I'll turn it over to each one here. So first off is Léon van Berlo. He's with buildingSMART International. He's the technical director. He has previously served a variety of roles at the National Institute of Innovation in the Netherlands, on the BIMserver project manager and senior BIM innovator. He's also worked on several open standards and BIM standardization initiatives for international audiences. And I'll turn over to him. Thank you.
Yeah, thank you. Thank you for having me. It's quite a pleasure. I noticed that the theme of these three presentations is a little bit how can we use building data and semantic web. So I've kind of focused on the semantic web part of IFC as well. But let's start with the beginning. So we are indeed talking about the exchange of building data. buildingSMART has a long history of BIM and open BIM. So usually there's a lot of these assumptions that we are exchanging building data, geometry with some additional information on top of that. But if you're exchanging just geometry, you obviously want to know more about the object. What kind of object is it? You want to classify it as something. But before you can classify an object, you need to agree on what it is. You need to have an agreed definition of what it is. So, for example, before you are going to exchange an object like this, we first have to agree on what this is. So in IFC, this is an IFC stair flight. And that's part of an IFC stair. And in ISO 6707, and therefore also in IFC, there's this whole definition of what an IFC stair is, including an IFC staircase, including an IFC stair flight, and a slab as a with a type landing. So it's all pretty well defined on what do we mean when we talk about a stair, how are we going to exchange it, what are the local placements of these individual objects, and even what type of IFC stair flight is this. There's a lot of different types of stair flights and stairs defined as well, including documented with pictures and everything. So IFC stair is not the only object that we want to exchange. So it's a specialization of a building element, which is a specialization of an IFC element. And that goes on a couple of layers. So we have this specialization layer. There's a lot of relations between the objects. And this goes quite far, actually, so far that there's 885 entities defined, semantically defined. A lot of different individual properties, and all of these things have additional enumeration types, select types, functions, property sets. There's really thousands of properties in standardized property sets. There's a lot of documentation on how this should be used in a certain spatial structure. So it's really about how are we going to exchange this in what kind of standardized way. What's unknown for a couple of people is that IFC serves a lot of different domains. So it's not just architecture and construction. There's a lot of MEP elements in there as well, HVAC, fire protection, and with the upcoming 4.3 release, there's also a lot of infra-specific entities. Also unknown is that there's this whole part of facility management, building controls. It's quite a rich semantic agreement. So in short, in a few sentences, what is IFC? It's a semantic agreement defining what something is, how we're going to call it, how is it connected to other things, what are its properties, how we're going to define geometry, etc., etc. So you can call this a standard, you can call it an ontology. Doesn't really matter to me how you call it, but that's what IFC is. And like I said, it is quite rich. Just sharing with you, leading up to the following presentations as well, that IFC is not just about doors and walls. There's a lot of different IFC sensor types in there. We have IFC irregular time series, data origin, external references, applicable date, you name it. There's really a lot of semantic richness in there. Not all of this is known, and therefore also not all of this is used. But when you really dive into the details and the specifics, you can find quite a lot on this. So we haven't talked about representations yet. So maybe diving in on that in this next picture. So the core way how we define IFC, all of these classes, relations, properties these days is being done in UML. So this is IFC 4.3. And then from that core UML model, plus some additional documentations and constraints, we are generating a JSON schema, express schema to exchange data and step files, an XSD, an IFC OWL, and potentially others as well. There's also experiments with HDF5, etc., etc. So this is kind of the the ultimate picture. We have a data model, and you can represent it in multiple different ways. When you want to have a very efficient file exchange, these step files is probably the best way to go. When you want to use it in a linked data environment, these IFC OWL is probably the best way to go. But this is a picture that works in PowerPoint, because in PowerPoint things always work. In reality, this central core model of IFC has a lot of weird quirks in there that are very closely related to this express language and the step technology, which is relatively old. So that influences how this core model is being represented in different languages. So because of these weird step and express modeling techniques, it is difficult to express it in a very nice way as XSD, and it's also a bit weird to express it as an OWL, as an ontology. And the problem there is because there's a couple of these very specific express things in there, like linked lists, but also things that we made up ourselves, like this IFC string or IFC URI reference. There is no real reason to copy these concepts into something something similar but different. See a lot of nodding heads on the webcam, so that's good, I guess. So this is really a problem for us at the moment. And that's also what the technical roadmap identifies as one of the biggest problems of IFC modernization at the moment. And you see this green line as the sweet spot. And we really want to take IFC 5 to a place where we can express the data standard into different languages relatively easily. So because of these weird specific things that are in IFC that are very difficult to express in other languages, you get alternatives. So an alternative for IFC is this bot technology, which for me is really a good example of the way forward. It replaced all of the IFC strings to normal strings. It removed all of the prefixes of IFC as well, stripped out a lot of the domains to make it more modular, stripped out a lot of resources, replaced that with other available things in on the link on the semantic web. Really good example, but this wouldn't have happened if we would have a better core IFC model. Something else is also this Ifc Json Initiative. This is an initiative inside buildingSMART at the moment, where they just completely stripped out the IFC geometry things. They just purely used the data model and then made references to OBJ objects to link the geometry to it. So they're basically stripping out all of these 15-year-old patched geometry kernel from step and replacing it with something that every online viewer can read. So I think these are really good examples. We're also internally working on experiments ourselves. For example, this digital twin for built environment, JSON-length data context and vocabulary. This is basically also just taking IFC, stripping the prefixes, reshuffling a little bit, really with the hope that people that want to connect to IFC or connect to definitions to use this one, because there is this assumption that IFC is just for walls and doors and windows, and there's not a lot of more dynamic data points in there, but there are. So we're, for us, this is kind of a desperate try to communicate that and to see how the industry responds to this. So zooming out a bit, so as I said, we have these geometry standards. We also have when you further define the geometry definitions with classifications and properties, you come into this one specialization layer lower, where you could say we have a stair or we have a sensor. These are the definitions. These are the different kind of types. These are the properties relations. But for IFC, that's still, we really want to keep IFC on this global international level. So we're not going to put in national classification systems or national specific property sets into IFC, because those should be extending IFC. We really want to keep IFC on a more generic level. So there are a lot of national classification systems that are kind of further specializing the classes in IFC. There's a lot of additional properties that are further defining and further extending the properties in the classes in IFC. So you get this layered approach of different standards that are not necessarily semantically stronger or weaker. It's just the scope of the standards depending on what the objective is of that standard. And IFC is very much trying to find consensus on a very global level. So just plotting in other initiatives like BRIC or Hvac. Please excuse me if you don't agree with this positioning here. Could be higher, could be lower. I don't really care. It's just about trying to position it a little bit compared to each other. I think bot is a bit more generic even because it kind of reuses this existing resources and things like strings and URI references. But it doesn't go as deep with all of the detailed classes and properties. Hvac, again, arbitrary, could be higher, could be lower as well. But just to give you an impression that there's a lot of different domain-specific agreements. There's a lot of generic agreements. And for us, for buildingSMART, the key is really to not claim that there will be one standard, not claim that IFC is the standard to rule them all, or whatever other standard there is, not even trying to get 15 standards together to get one new one, because the end result is that you have 16 standards. The key is really to try to link them to each other and try to create interoperability in that way. So as an example, in our industry, we have a couple of these bigger classifications or even standards like ETIM, Omniclass, Uniclass, some national material database, whatever. And instead of them competing with each other, we really hope that those will be connected to each other, refer each other. And IFC then is just one of the standards that can be referred to. Again, not higher or lower in any kind of hierarchy semantically. So the way we're trying to do this is with the buildingSMART data dictionary. And that also has a long history. So if you've heard this before, please reset your mind on this and have a fresh look. buildingSMART data dictionary is for us really kind of an easy way for the industry to publish their standards in a linked data environment. So it has a graphical user interface. So when I search for sensor, I get a lot of results in IFC, but I can also get results in ETIM, Uniclass, etc. And all of these publications of ETIM and Uniclass can also refer and link to each other. And that's because every object in there and every property has unique URI, and it has the ability to link to other URIs, also outside the BSDD. I want to make that very clear. So this is not one database that is closed again. We have examples in there of entities that are extending other published classes that are not even in the BSDD, but we just use this URI system from Semantic Web. Currently, we have this graphical user interface, a JSON interface, and a GraphQL interface. We've got about 20 different standards in there, including IFC, and we're adding this RDF interface quite soon. So there's multiple ways to interface with this, with the BSDD, based on these URIs. Really hoping to get Rick and Hvac and maybe a couple of others in there as well. So open shout outs to have a fresh look at this. So yeah, wrapping up. I think I'm also running out of time here. IFC is not just a file format. It really is a semantic data standard that can be represented in multiple different ways. We are struggling to represent it in other ways than this step and express file format, but that's really on the technical roadmap and a strong focus. And the kind of the first hints you see of that new strategy, for example, is how we are dealing with the buildingSMART data dictionary, how we're trying to link different standards together there, how we're really leveraging Semantic Web also to improve this interoperability. So that's a very high level overview. If there's anything you want to remember from this, then please remember that this is an open call and a shout out for collaboration to really improve IFC, to modernize it more, to get it more onto the Semantic Web. We have a clear strategy, but we have limited resources, so everyone is very welcome. And please, this is not a joke. I'm Dutch. I'm used to getting interrupted mid-sentence and being having colleagues that are very direct. So please reach out to me directly. Looking forward to it. Thank you very much.
Great, thanks, Léon. We have time for one question, probably, if there's a quick question out there. Otherwise, we'll hold off until the end for other questions. Go ahead, you should be able to unmute yourself and ask a question directly, or go ahead and put one in the chat. Okay, I'm going to go ahead and move on. If there are questions, feel free to put them in the chat, and hopefully we'll have time at the end for more questions. Léon, thanks again for your presentation. You definitely covered a lot of ground, and I'm sure everyone is overwhelmed with how much you just threw at us. So moving on here, Joel Bender will be talking about semantic web models. And so Joel Bender is a programmer and analyst at Cornell University. He's a senior developer for the Energy Management and Control Systems, which is a cluster of systems that supervise the building automation and control systems on campus. He's on ASHRAE's 223 committee on semantic data model for analytics and automation applications in buildings. So go ahead, Joel, take it away.
All right, thank you very much. All right, so you've probably all heard about Bacnet. It's been around for quite some time now. It's a very popular, widely supported communications protocol for building automation systems. When someone first looks at the standard, it's 1,400 pages and can be pretty daunting, but the basics are actually pretty simple. So for folks that are not familiar with ASHRAE, it's the American Society of Heating, Refrigerating, and Air Conditioning Engineers, and is an accredited American National Standards Institute publishing organization. So ASHRAE standards become ANSI standards, which in turn through the liaisons to ISO become ISO standards. So this is it's been a long and a lot of fun process for building this protocol. So it began here with my colleague and former boss, Mike Newman. And we've been involved, very actively involved with it at Cornell ever since. So at its core, Bacnet is a communications protocol between devices that contain objects which are bundles of properties. And when those properties are metadata elements about the object. The most common properties are object identifiers, object names, status information, and for some things like analog or binary value objects as a property called present value. So at its core, the point of Bacnet is to be able to communicate in a standard way across a variety of different types of building automation control systems, sort of the brains pieces. Bacnet objects have a very small collection of required properties that every vendor is required to support, along with a variety of optional properties that can be implemented by vendors depending on the capabilities of the project of their platform and the application that they're targeting for their particular kind of controller. The presence or absence of certain properties can dictate some types of behavior. For example, if something has a priority array, then it's considered commandable. To assist with integration, Bacnet objects have standardized metadata properties like this special one called a property list property that can reflect what is being implemented in a device. So you can pick a device, plug it into the network, and using standard sets of services, find out what is going, what kinds of capabilities that device provides, what kinds of objects, and what their names are and how they're related in some loose sense. Okay. So the services in Bacnet, so we in the Bacnet protocol, we break these into objects and services, and the services are collections of communications messages that are similar to like what some people would consider a remote procedure call, where a device sends a request, gets back some kind of data or a simple acknowledgement. There are services for this device object and property discovery mechanisms for reading and writing values, subscribing and receiving change of value notifications, uploading and downloading files. And that's all of these different types of services were included in the standard and extended in the standard over the last 20 years or so by requirements of the industry. So this is a case where vendors come to ASHRAE and say, we would like the opportunity to be able to generically back up and restore our devices over the network, and we'd like to be able to do that in a standard way. So that those kinds of proposals go in front of the committee, they get negotiated around and then voted out as addenda to the standards. So all of the things that you see in Bacnet have been provided by some industry support for wanting that particular type of service. All Bacnet devices are peers. They can initiate and respond to requests all by themselves without central workstations or servers. And so when you hear about people discovering a Bacnet device, object, or a service on a network, they're using very simple read requests to get the metadata property and learn what's available. Pretty early on, the Bacnet committee was split into smaller working groups that were focused on one particular aspect of the protocol. So most active groups have been recently the IT working group, which is responsible for the Bacnet Secure Connect protocol. The Network Security Working Group is on authentication, authorization, and auditing topics. And the Data Modeling Working Group is responsible for exchanging Bacnet models in a variety of formats like XML and JSON, and it has worked on other things like web services. So a few years after Bacnet was published in 1995, there started to be a wide variety of general purpose and application specific devices. For example, a variable frequency drive controller and variable air volume terminal units. And while it's relatively simple to know what Bacnet objects are defined in a device, the object name and description are just simple character strings where the content is left up to the vendor, or in some rare cases, coordinated with naming conventions created by the customer. So it's simple to understand what's there with respect to a device, and it's very difficult to understand what it is when examining any specific type of object. In some cases where the object names are like AV010, you needed access to and training in the vendor-specific device configuration to be able to understand what it is. You actually had to get into the device to understand it. Even 20 years ago, we identified this process as tedious and time-consuming and error-prone. So in 2004, there was an effort to create profiles of common specialized devices so that either the names and descriptions could be standardized within a family, or there could be some additional metadata for determining if a vendor's controller had some specific kinds of objects to match the profile. And this work was given to the Application Profile Working Group. That group split into basically two different flavors of activity. The first ones were for things like lighting objects, which was given to the Lighting Working Group, which is made up of vendors that specialize in lighting applications. Elevators, lifts, and escalators were given to the Elevator Working Group. So in those cases, the collection of standard, what I would sort of consider as basically primitive types of objects, of just reading and writing just simple analog and binary values. These other more advanced objects in some higher level sense, because they include a lot of specific application specific properties and behaviors. The other piece of this was that the Application Profile Working Group provided a generic underlying framework that could present a wide range of other profiles, which led to two important additions to the standard. Something called a structured view object, which describes a hierarchy of collections of points, and a tags property that's available to all objects that's a list of name value pairs. In this case, tags is very similar, but has some important distinctions between that and Project Haystack tags. But the basic idea of using specialized names to help classify objects within a Bacnet device sort of stays the same. So with these pieces in place, the required and optional components of a particular profile could be created by both application domain experts and by vendors creating extensions to standard profiles to be able to market their distinguishing features. So with Bacnet devices being the brains part of a cyber-physical system, it's a challenge to put any one specific system in the context of the other systems that are in a facility. Even with the so-called like smart valve or a rooftop unit or something that comes as a bundled package, even if all of that content is completely consistent within itself, understanding and analyzing the behavior of that for advanced applications like fault detection and diagnostics needs some way of referencing other devices. And this is where the semantic web and the linked data comes into the picture, along with many efforts over the last 5 years to create models of building systems. So these, the AP working group was transformed into the Semantic Interoperability Working Group, and it's given its own ASHRAE Standard 223, currently P for proposed. So the intent now is not only to be able to help satisfy the concerns of the Bacnet committee, but to try to extend those into modeling that might be useful to other kinds of activity. So the Bacnet SI working group started with already published standards by the World Wide Web Consortium, namely the Semantic Sensor Network Ontology. which includes the sensor observation sample and actuator core ontology, the building topology ontology, which is published as a draft from the link building data community, and other things like the Web of Things working group, real estate core, brick, and haystack. So smart energy aware systems is an ontology published by the ITEA, a European organization, and the smart applications reference ontology is published by ETSI, which also contains concepts and systems descriptions in the energy management and control systems domain. So those have been included in our working group study. So the brick ontology and its community members, which will be presented by Gabe, have been very active in the SI working group, and have not only helped guide its design, but provided tools and software to validate the model during its development. So unlike other standards within ASHRAE, this one is working on example models and building the documentation that will be part of the published standard right out of the model. So that's fairly unusual. And thank you, Leon, for the description of the work in the buildingSMART community. Hopefully we can get these efforts collected together more closely. So the original AP working group started with a profile for variable frequency drives as a sample domain because they figured that it was fairly limited, and the committee could work together and wrap its head around what that was, sort of identify what the individual pieces were. As this has changed over into the Semantic Interoperability Working Group, we've started with Guideline 36, ASHRAE Guideline 36, which is high performance sequences of operations for HVAC systems, to leverage that group's work on precisely describing the components of a particular system, such as variable air volume terminal units, and a few variations of the systems, and the specific lists of inputs and outputs and key performance indicators of those systems. So for example, this particular simple VAV terminal unit, along with is presented as a control system schematic. And we can right away model this as a system or collection of devices of how those are connected to other systems. And these can be recursively defined with finer grain detail of the devices within a system and internal connections between devices. And then those properties of those devices corresponding to analog and binary inputs and outputs. So now we have an association between a specific systems topology as presented by a controls schematic and the components that are necessary to be able to present that content over Bacnet to be able to read and write those values. So now the next piece is relatively simple. We give each one of those an individual component, a unique identifier within the graph, and then we can build a graph of these relationships between elements. So this RDF graph is used in our case to precisely place the property of a system, such as the temperature leaving a unit, to unambiguously in the topology of the system itself to assist with classification of what that particular property is. So one of the challenges in our industry is that a lot of people call the same thing by different terms. So by going down to what we would consider sort of the ground floor of how these systems and components and properties are laid out, we can provide a hook that other types of ontologies, specifically brick, and in some senses the building topology ontology like BOT and real estate core, and maybe even project haystack can help leverage. So even in cases where there's systems of systems like this one with an air handler, multiple VAV terminal units providing air to different zones, it's relatively easy to build these graph models with appropriate tools. And the Semantic Interoperability Working Group has been developing these tools to build these models and test the standard while the standard is being designed. So in this case, you'll notice the hot water system contains boiler and preheat coils, preheat and reheat coils, where the coils are also parts of other systems. So these things can be nested. The analysis of one particular kind of system can extract those pieces out of the model for its own analysis separately or in conjunction with the other components that it's linked to. So in addition to Bacnet, which is ASHRAE 135, there's an additional effort to design a controls description language in ASHRAE 231, which is a combination of graphical and text-based programming derived from Medallica. So there's over 100 of these elementary blocks that can combine into composite blocks and extended with proprietary blocks. So this particular effort, funded by the US Department of Energy, has provided for funding for a wide range of software developing these digital twins for simulating buildings and comparing the data from real buildings to these models for what we would consider actionable insights into fault detection and energy consumption. You're probably familiar with the Open Studio software, so that's part of this family. One of the important efforts of the Open Building Consortium that's leading this piece is that the sequences of operations that are in Guideline 36 have been modeled in Medallica in some cases, so they have been in some sense proven that the sequence will operate as expected when it's implemented in the real world. So now the effort is, how do we take these sequences of operations out of Guideline 36, build models of the schematics of the systems, line up those properties, and line up those values with the simulations. So with a clearly defined model for Bacnet, which is my orange piece here, and the semantic interoperability model for closely coupled systems in the blue along the bottom, and a functional model for running simulations and downloading into real world controllers. The next step for the semantic interoperability working group is to clean up this spider web in the middle of this figure, which is the associations between models. One of the important pieces of putting this puzzle together for Cornell, in addition to continuing the Bacnet work that began here, is to bind together the key performance characteristics of building assets and along with the asset management systems. So the mechanism of using these, of building these together into a graph is not just the graph for a graph's sake to help applications within the graph, but to help link it to other enterprise systems that can also be represented in the same graph and that they can cooperate together. So for example, if we have a building topology ontology model of a facility that is associated with multiple departments on campus, then we can find out what kinds of activity in the rooms corresponds to activities of the members of the department and how they impact energy within a facility. So you can't do those kinds of things without building these larger, more tightly coupled graphs. We'd also really like to be able to provide a standard building model to analytics companies where they can provide operational insights to run our facilities better. So if I can take a model of one of our facilities that contains the model of the Bacnet topology, then I can provide the telemetry data for that facility along with the model, turn it over to a company. They can analyze the graph, analyze the content, and return back some important insights for us. So before I turn this over to Gabe, if you'd like to join, we'd love to have you. You don't have to be an ASHRAE member to join, and certainly not some kind of protocol geek or ontologist with a background in philosophy or semiotics or morology or any of those other tabby things. Just feel free to join us in the Google group or send an email to the working group convener or myself, joelbender@cornell.edu. And thank you very much for including me. This has been great. Any questions?
Thanks, Joel. Yeah, I think we have time for one question, if it's a quick one.
Fire away.
And I think everyone is overwhelmed.
These talks are all just so complete and good.
This is great. As
Oh, you ain't seen nothing yet.
This is great. If there's any questions, again, feel free to chat. Hopefully we have a couple minutes left at the end before we have to adjourn. So lastly here, Gabe Fiero from the Carter School of Mines at NREL will be presenting. He's an assistant professor of computer science at Carter School of Mines with a joint appointment at NREL. He works at the intersection of databases, systems, information modeling, data science, and built environment and the Internet of Things. His research interests are broadly in designing, building, and deploying systems that enable sustainable practices by making data easier to discover, manage, and leverage. Go ahead, Gabe, take it away.
All right, thanks for that introduction. I couldn't have said it better myself. I think that's the intro that I wrote a while ago. Hi everyone, so I'm going to be talking about the BRIC ontology, and in the context of building data exchange, the kind of data that I'm talking primarily about is the telemetry coming out of the BMS or BAS or EMS or whatever three-letter acronym you choose to use. So I'm sure it's no surprise to all of you that there's an increasing amount of building data available, enabling new kinds of data-driven processes, not just automated fault detection diagnosis, but whatever a digital twin happens to mean to you, new control schemes, predictive maintenance, interesting data-driven applications. However, that data is really, really hard to access and use, especially at any sufficient scale beyond n=1. A survey on Kaggle of data scientists in 2018 found that even in these sort of well-curated data sets where there's a table somewhere in a database, data scientists spend upwards, of 40% of their time discovering and understanding just what that data is. And in a building, it's not exactly, the state of the art to have extremely well-labeled and curated and consistently modeled data sets, because they all look like this. They are all, whatever engineers, had to squeeze their descriptive labels into these 16-character SCADA tags or to represent all of this complex context of what these things are, what the data sources are, whether they input or output, all the rest of that. You have to squeeze all that information into a point label. And the result of this is these ad hoc and inconsistent naming schemes, even if there is a pre-existing tag dictionary. And even if you did have some structure to these names, not only are they going to be different to all of these buildings, but they still don't make all of that necessary information explicit about what is this data source, where is it, what is it doing, what is it relevant to. And just to look at an example, here's my favorite point label example from a building on the UC Berkeley campus. The building's name is SODA, which you would actually think that SOD at the beginning is the name of the building, but actually only the first three letters are the name of the building. Then the A means that there's an air handling unit, it's got an ID, there's a zone or a room, there's an implied VAV box that's not anywhere inside that point label. You have random, size delimiters to pad it out to the correct length. And then finally at the end, you have a little acronym that tells you what exactly that point is, which of course implies that there's some thermostat somewhere, and who knows where that thermostat actually is and where it's actually sensing data. And so what do we need if I'm gathering all these points and all the data that's coming out of these points in my building? What do I need in order to consistently exchange that data, to be able to author data-driven applications over tens, hundreds, or even thousands of buildings without having to figure out this messy parsing for each individual building? And what you need to do that, we believe, is you need to consistently organize the things in the building, for some definition of thing, by their sort of type or class. You need to capture the relationships between them, how they are connected, how they relate or influence one another, and you need to capture the necessary properties of those things. And so the effort that I've been involved with since 2015, when we got this started, is the BRIC ontology, also called BRIC schema. And what it is it is a linked data model that describes the entities in a building and the relationships between them. The way that we, another way of saying linked data is you can say it's a graph based, it has nodes and edges, and those nodes and edges have labels, and I'll show you an example a little later on. And so, we're going to describe not just the physical things, but also virtual things and logical things that are there. We're going to describe them using this class hierarchy, describe the relationships between them, and ultimately get to the point where this graph structure is going to provide some context for the data that we're storing in a time series database or an analytics platform. So how something like Brick would fit into this picture is you have your actual building subsystems and data collection. This may operate over a Bacnet network or LawnTalk or OPC or whatever, whatever you have. You have this metadata graph abstraction, which is going to provide a structured representation of those data sources, the equipment they're associated with, how that equipment is associated together and connected. The live or historical facility data will be linked to that graph. And together, the combination of the live or historical data and the graph abstraction is what's going to enable those applications. And what Brick is specifically just that metadata graph abstraction. Brick is agnostic to how that data is pulled out. It's agnostic to a certain extent to how those applications are actually authored or where you actually store your time series data. So a quick example of what a Brick model might look like for a very simple HVAC system. We start with the entities themselves, each of the labels that you might pull out of the BMS. Or out of a blueprint. What we do is we associate a type with each of these nodes. That type is pulled from the ontology definition, so it has not just associated set of tags, it has rules that dictate how it can be correctly used. It has a textual definition that tells you what it is. And then we have the relationships between those nodes, between the entities that say, well, you know, at the top, we've got this air handling unit. It's going to feed into these two VAV boxes. This VAV box has feeds into a zone, which consists of these rooms. This other VAV box has a set of points associated with it. It also has a damper, which in turn has its own, positions, set point associated with that. And so where do those types come from? We've got, I think, over 700 classes defined. That's growing every day. We have people constantly submitting suggestions and edits to that hierarchy. So we've got the points, which are the sources and sinks of data. This is sort of the classic notion of a BMS point, sensors and set points and alarms and commands and parameters and whatnot. We have equipment spanning HVAC and lighting and electrical subsystems and security subsystems. And we have locations. Not just physical locations like a building or a floor or a space, but also logical locations like an HVAC zone or a lighting zone and things like that. And so each of these hierarchies or structures has been designed to be extensible, and they do grow over time. And to then touch on how these things can be related, and this is definitely something you can go back and look at. We have all the these diagrams all on the Brick website. You can see how types of things can be related to one another. And this is far from a complete model of the building. We're not trying to make a better IFC or anything like that, but rather focus on what are the salient relationships that are really important to understanding what a data source is and what it's connected to. So we can see the relationships we have here are essentially the association of data. That's the is point of. We have the physical location of something. That's the has location. We have composition, which is has part. And we have sequence, which is feeds. And by and large, those are the high-level relationships that you really need to be able to talk about how a building subsystem is put together. We've also been introducing entity properties in a recent version of Brick, and these are the sort of static nameplate attributes of equipment that can be associated with each of these. This could be the unit of measure for a data source. This could be the rated power output of a VFD. It could be the net or gross area of a room. And there's a growing set of these that allow us to annotate these Brick models with consistent expressions of certain characteristics of these devices. And so we've got our Brick model. We know where the classes come from. We know we can annotate these entities with different properties. And for any property of it that really changes over time, for some definition of change and some definition of time, that stuff is going to go into some time series database. And what the Brick model will do is link between the entity expression in the metadata model and where that data is stored in your actual data historian. The way that's done is essentially using encoding a foreign key relationship. So my entity ZNT101, I have both the brick expression of its type, it's a zone air temperature sensor. There'll be other properties here like its units, maybe its reporting rate, the date that it was installed, things that you might pull out of a asset management system and represent and link into the brick model. It also has that time series identifier, and that time series identifier is what you would use to go fetch the data from your corresponding store. So this could be a SQL database, it could be Influx, it could be a bunch of CSV files and a file share somewhere. We're really not super specific on where that can be, so we're very flexible on that point. And so the way that works, the way that you would use this to build an application is you have two databases. They may be the same physical database, but it's useful to think of them as two logical databases. The brick model database, which contains the metadata representation of the building, that's the graph, and the time series database, which stores all of the telemetry. And what happens is when you're writing an application, you express the data requirements of that application using a SPARQL query. And SPARQL is the standard RDF query language for those types of directed graphs. So this is the same query language you would use for 223P or for BOT or for Real Estate Core or anything like that. This particular query is expressing, I want the mixed air and supplier temperature sensors on either side of a cooling coil, and I want the cooling coil valve position so I can tell if when the valve is open, I should see some cooling of the air downstream if everything is right. The execution of that query on the brick model database will give you essentially a table of results. So each of these rows will be the name of the air handling unit, the name of the mixed air and supplier temperature sensors, the cooling coil valve name, and then the name or the ID of the position sensor for that valve. For those things that are points, you then use those data points to go, use the results to go look up your data in your time series database, and you can get back your data frame or your matrix or your CSV file or whatever you need, and that you can go and hand off to your data ecosystem. And if you look on the Brick website, we actually have videos of demonstrating this live using timescale DB over Postgres and an in-memory Brick database. So there are live examples and real examples of how you can do this. Another thing that we've been doing in Brick, just as in 223P, is how do we ensure that the way that this model is put together has some regularity to it? And the way you do that is with a thing called a shape. And what a shape is it's a set of constraints or rules for how something should appear in the graph. And so for this brick model here, a VAV feeding a room, and the room has an area property with units and a value. We might define a manufacturer-specific shape that says, well, if it's a model XYZ VAV, it should have these points and it should be connected directly to a room. We might define shapes that are specific to a particular site that says, in this particular site, we actually know the exact square footage of each of the rooms. And so each instance of the room class in this brick model for this site should have an area annotation present on it. And then we can also define regularization of how brick is actually used. And brick can say, when you want to talk about the area of a room or in the area of a space, you need to have a unit and you need to have a value. That value needs to be numeric, and that unit needs to be one of feet squared, meters squared, or something similar. And we're working towards having libraries of these shapes that you could download from OEMs or vendors or analytics libraries or even standards organizations. And this is one of those ways where we're going to be able to bring Brick and 223P close together and make sure that they're consistently used together. And to speak of how they would fit together, I apologize for the crude diagram. I was trying to figure out a good way to visualize this, and I couldn't think of one, so I just did the most straightforward thing I could sort of muster. And so at the bottom, you have your existing metadata sources, the BMS labels, your BIM, the OEM provided files, human annotations, whatever. Through direct translation or statistical inference or active learning processes from those existing sources, you could produce a 223P model or even a brick model directly. A 223P model would then be able to automatically produce a brick model from its description. The intent for BRIC in the context of this whole thing is to enable the writing of these data-driven applications by naming and formalizing the concepts that people are already using when they talk about these applications. In 223P, you would have the expression of a damper. You would know what it's connected to. You would know the direction of the air through it. You would know all these detailed properties about how that damper is put together. But there isn't necessarily a hard and fast rule that you could write down that says, is this damper an exhaust damper or not? Or is it a supply damper? And what BRIC does is provide that higher level vocabulary that's closer to the application space to make it easier to find that data. But it can always be rectified and more formally modeled by building on top of the 223P model. And that's part of my interest in being involved in the 223P effort as well. This is the last slide. How to get involved. We are always looking for people to help out, give us feedback, let us know, what works, what doesn't work. brickschema.org will be your sort of entry point for all of that. There's a community forum and mailing list. It's all open source. There's directions on how to contribute. And there are weekly working groups, both European, US, and Asia friendly times. So please check those out. Definitely feel free to send me an email or check out my website, gtf.fyi, if you have any questions. And thank you very much.
Thank you, Gabe.
3 whole minutes.
Yes, let's do it. Questions? Okay, don't be shy.
There's a question in chat. I think it just came to me. Is it possible to apply machine learning with BRIC schema?
The high level answer is yes, 100%. A lot of machine learning processes, if you look at any paper, it's going to rely on having some well-structured data set that you can feed into your deep learning pipeline or your decision tree. And where BRIC would fit into that is, how do I get that data? How do I figure out what data I actually want to input into my machine learning algorithm? And so that slide I showed where you would write that query that says, give me all temperature sensors in the buildings, associate them with rooms, with which ones in the same HVAC zones, what are the related points for equipment feeding in. You would write the query to discover the data and then pull the corresponding data from your time series database and then feed that onto your machine learning algorithm.
Could I ask a question?
Go ahead.
Oh, sorry, it's not a good camera view. So I've seen this before, the concept of having the building data in a graph and the time series sensor data in a time series database. So that would mean you would need to write 2 queries in each case, say a SPARQL query for the graph data and then some sort of SQL query for the time series data. And in my head, I have it that I'd like that to be just 1 query. I'd like to write, say, just a SPARQL query that could capture both the graph data and the time series data. So I could write something like, in these particular cases, find me all instances where the temperature is higher than 25 across multiple sensor streams. Is that a good goal to aim for, or is it just not feasible? Does that make any sense?
Well, there's commercial products that allow you to do that. What they do is they take their relational database and they map it in as a set of tuples or a set of triples into the graph, right? So basically, it would take anything out of any relational data model, and it would take a row and turn that into an RDF object and take each one of those columns and turn it into a predicate. So then when you write your SPARQL query, you actually have no idea that in the back end, you're actually making SQL calls external to the graph library.
Oh, that's very interesting. I didn't realize that. I have tried converting time series data into RDF data, but it gets massively huge, massively quickly.
Yes,
It's
that's
not very
Yeah, that's definitely one way to do it. I would not recommend that way. It's usually easier to go the other way. So there's definitely work on sort of novel query languages for doing the hybrid of the two. The angle that I'm particularly interested in is if you wrote sort of pre-wrote Sparkle queries that could populate tables in your SQL database. And that table might contain, oh, here's all my VAVs and all the relevant attributes and maybe a couple links there. Then I could just write just a SQL query and it's actually executing over RDF data in the backend. But I don't necessarily have to worry about all that flexibility of structure. And so if you're using things like shackle shapes to bring some regularization to how that graph is formed, then it actually becomes pretty easy to define those tables. But definitely something where there's a need for good high-level query languages to make the stuff easier to use with time series data.
Okay, that's brilliant. Thank you very much.
Yeah.
Thank you.
I also put a link in the chat to the demo that I did. There's a video there of how to use Sparkle queries with a SQL database. It doesn't quite do filters on top of values in that simple example, but it gives you a very basic framework on which you could see how some of that stuff might be implemented.
Brilliant. Thank you.
Great. We are at time, and I want to respect everyone's time here. So I want to wrap it up. Thank you, everybody, for attending. Thank you to our presenters for presenting. If there are follow-up questions, please feel free to reach out to the individual presenters or to anyone at BIPSA and the Building Data Exchange. There is one more question that just popped up in chat. I will let you answer that, and then we'll call it out. We'll call it a day. So it says, when do you expect 223 to be released?
Yeah, so 223 is grinding away. It's a committee process. So the interesting aspect is it uses both vendors and users and government participants. So getting all of them to collaborate is quite a challenge. I would expect that an advisory public review of 223 will be available in the spring. So probably not in the balance of this calendar year, but in the next couple of months after that. So it usually the process is it goes through an advisory public review. We gather the feedback from that, find out what kinds of changes we need to make, and then go out for a 45-day public review, which is a much more formal feedback into the thing. And then assuming that we can resolve all of the comments from that, then it becomes published as a standard. So there's lots of opportunities. There will be lots of opportunities to view what the publication is supposed to look like and have feedback into that. And if you'd like to jump on the gun, then I would encourage you to join now.
Great. Thank you, Joel. Thank you, everybody. And thank you, BIPSA, for hosting this. And yeah, have a great evening, everybody.
All right. Thank you, Nick.
Take care, everyone.
Thanks, everybody.